from the university. And particularly this topic, what we say, the water, food, energy nexus, it's very important for all countries, like similar countries like India, not only India, for many countries. The reason is that water is life. Okay, in fact, UN has itself declared a 10-year period as the water for life for 2005 to 15. And when we see that the amount of water we are spending for agriculture across the globe, 70% today we are spending for agriculture alone, which is going for the food, and it has a lot of energy implications. And today we are experiencing very severe variations, okay, climatical reasons and climate change, and also we are getting experiencing the droughts and sometimes severe floods. So in order to cope with all this, we need to have the proper comprehensive understanding of this nexus, water, energy, food nexus. And ICID is one of the international organization in which Dr. Raghav plays a very key important role as being the president of International Commission on Irrigation and Drainage. So in fact, when we requested Raghav for this particular cause, he immediately accepted, and I'm very happy for inviting Dr. Raghav for making the presentation today, because this is very important concept and discussed at different forums and policy levels. But now in order to take it to the field level, it is very important to understand its basic concepts and go forward. In fact, understanding and acting upon the dynamics of this water, energy, food nexus is critical for sustainable development. I am sure that we are going to get benefited from the talk of Dr. Raghav today. I welcome you all on behalf of this university and also my personal behalf for this important lecture. Thank you, Dr. Raghav, for accepting our invitation and making yourself available for today's talk. Thank you very much. Thank you, Uma.
Thank you, sir, for your valuable words. I'm profusely elated to introduce distinguished speaker, Professor Raghav. Professor Raghav is UK Center for Ecology and Hydrology Fellow, hydrologist and water resources management specialist. He has long experience of being employed by both universities and research centers. He's an expert in catchment hydrology, irrigation, drainage, soil hydrology, soil physics, soil, water, plant, atmosphere relations, impact of land use and climate change on water resources, water and food security, and drought management. His research interests include building cross-sectoral collaborations to understand the dynamic interactions across water, energy, food nexus using new scientific knowledge to help stakeholders set objectives for freshwater management and transforming science into management solutions. And also, his research interests include improving water productivity and water use efficiency, irrigation and drainage management, agricultural water management, soil physics, soil hydrology, remote sensing application in hydrology, hydrological modeling at catchment scale, quantifying the impact of climate and land use changes on water resources, identifying the gap between water supply and demand, and suggest management solutions to narrow the gap, and water, soil, and fertilizers management modeling and experimentation at field scale. He is president of International Commission on Irrigation and Drainage. He was the vice president of ICID during 2010 to 2013. He was the chairman of the Permanent Committee on Strategy and Organization of ICID 2010 to 2014. Chairman of the Working Group on Water and Crops, ICID, and was the chairman of British National Committee on Irrigation and Drainage, ICID, during 2007 to 2011. He was the founder of Working Group on the use of poor quality water for food production in ICID. He is an international advisor to a number of organizations like Brazilian National Institute of Salinity Studies and to King Saud University, Saudi Arabia, and also UNDP. He is lecturer and external examiner to various universities in and outside the UK. He is a recipient of several international awards, reviewer for more than 15 international journals, and evaluator for several funding organizations. He is author and co-author for numerous scientific papers and editor and co-editor of several special issues of international journals as well as conference proceedings. He is a member of editorial boards of 4 scientific journals. He developed 2 widely used models, SALT-MED, SALT-MED for field scale as a tool for integrated management of water, soils, crops, and nitrogen fertilizers. And another model is IHMS, Integrated Hydrological Modeling System for catchment basin scale. Thank you so much, Professor Raghav, for accepting our request. We are so lucky to have a resource person like you in this meeting. With all due respect, I request Professor Raghav, sir, to present on Water, Food, Energy Nexus, the integrated management for efficient use of resources. Over to you, sir.
Okay, I would like to thank you for this generous introduction. And I would like also to thank Dr. Komar Reddy, the Dean, for inviting me, and for also Dr. Yala Reddy, the Vice President of the International Commission on Irrigation and Drainage, for facilitating this invitation. It's my pleasure to talk to you today about that Nexus. And without any delay, I will start sharing my screen. So my talk really will be focused on the Nexus, and I will start by saying why actually we need to pay attention to the Nexus. Water, energy, and the food are among the most important and essential resources for life. Although a significant progress was made to enhance the resources efficiency and reduce losses, still the demand for these resources is expected to increase due to population growth, change in lifestyle, climate change, and the other aspects of global change. Thus, an integrated management of water, food, energy nexus is really essential. Water is needed to produce energy, and energy is needed to extract, distribute, and treat water. Food production requires both water and energy, and that's why we need Nexus. The water and energy food nexus approach is a more holistic vision of sustainability that recognizes this recognizes and tries to strike the balance between the goals, interests, and the needs of people and the environment. The increase of global energy demand is expected to increase by 30 to 40%, and the global food also to increase by 70% by 2050. By 2030, we also expect to have a gap between water supply and the demand, and that actually would be the rationale behind why we have to adopt the Nexus in our management. In the old concept of water productivity, we're only looking for more crop per drop. Since we started to think about the Nexus, we added now the energy, and now we have a new concept, and it says that more crop per drop per kilowatt. So there's a change now in our way of thinking. The Nexus the Nexus can stimulate the innovation and the use of new technology. For example, if increasing irrigated land is limited by the available energy, the authority might think about adopting non-conventional innovative energy sources like hydropower, wind power, or solar energy. So it is really motivation for innovation and bringing ideas. In addition, the Nexus could also lead to better governance arrangements via cross-sectoral water, food, energy frameworks and policies. Instead of only using one sector, we should involve several sectors. It could also lead to developing integrated management models rather than single-use models to account for the three elements of the nexus, and also to account for the impact of climate change and population changes as well. Uh, there are several nexus and a survey of 37 research on Nexus worldwide. They proved actually there are people, they have different arrangement for the Nexus. Some people, they talk about water and food only. And some people, they only consider water and the energy. And some people, they consider the water and energy and the food, while others, they take into account the climate change. 37 research across the world, it gave actually the water, energy, food around 11 out of 37 research, and 12 more about water and energy, 6 about water and food, and 8 about water and energy. So the water energy and the water energy food are the highest type of research worldwide. And also some people started to look at the scaling issue, because we can work on micro scale, that from a city or a town, and we take the scale into account until the macro scale or national level. And because at every scale, the requirement, investment is quite different. And for that reason, you have the scale issue with the Nexus, and how we analyze the data and how we actually integrate the different elements of the Nexus, starting from the city level to regional level, national level, to transboundary level. And at each point, there is a different trade-offs and different institutions and different stakeholders. The Nexus management objective is mainly to minimize the total cost of energy supply for electricity generation, cost of electricity generation as well, cost of water supply, cost of food production, and the cost of CO2 emission abatement. Water, energy, food nexus security is threatened right now by both the climate and social changes. And the challenges now that the Nexus is facing is actually mainly due to limited water resources. So we have to use that water more efficiently than it is now. So water use expected to increase percent by 2050, and irrigation about 70% of freshwater resources. The competition between biofuel and food for land and water resources is also another challenge. The other challenge as well is that we expected to double the food production by 2050 to feed 9 billion. And the climate change is projected to increase vulnerability of agricultural sector in most developing countries. The energy productions carries expensive water bill and associated with pumping, treatment, and desalination of water. Energy production in some parts of the world accounts for up to 45% of water withdrawals. Increased global energy demand by 34 to 40%, and the global food demand by 700% by 2050 is quite a big challenge. By 2030, we expect a 40% overall gap between water supply and the demand. The interdependence of and interrelationships were well known actually quite a while ago. So the concept of the water and the energy is not really as new as most of people they think. From the early civilization that we started, where the civilization started basically beside the large rivers, like the early civilization in Egypt by the Nile, and the civilization in Mesopotamia near the Tigris and Euphrates, are all these civilizations started beside really the water. And the optimal use and use of resources more efficiently were not really pressing issues at that time during because it was really plentiful resources and there was no shortage of any of the resources available during the early civilization. But the three elements were actually known to the early civilization. So this is example of how the early civilization started to extract water from the and uh, and you can see here that early civilization in Egypt as depicted on the temples that the farmers were getting water out of the Nile and they started to use more sophisticated technique to get water out of the canals and after that they started to use the water wheel and using a different energy instead of man power they started to use the animal power and started to use after that the pumps, diesel or solar fuel, and of course things started to move from there onwards to use more sophisticated technology. The water in the aspects of Nexus in 1950 we had 12,050 cubic meter per capita, and we expect 2050 that amount to reduce by to one third. So we expect the share per capita worldwide to be 4,500 instead of 12,000. And if you look here at the population growth and water withdrawal, they really parallel. So increasing the water and water withdrawal always associated with the increase of population and also the demand on food and also feed. And if you look here at the population growth worldwide, that we can see here that 1950, the number of cities more than 5 millions were really, you can count them in your hands. But now by 2015, that number of cities that really they have been growing with more than 5 million inhabitants is now really quite a lot, and some cities are really over 20 even million inhabitants, and that's puts a lot of pressure on water resources. This is something that I have been working on in some European funded project where I looked at the population increase and the decrease in the groundwater level. And this is examples from Crete Island that belongs to Greece, and also another one catchment in Guadiana Valley in Spain, where you can see there is a huge drop due to the increase in water production and population growth and the over abstraction of groundwater to feed the new population. And if you look here at some countries from the Gulf area, where simply they don't have rivers, these countries, so they rely very much on the groundwater. And you can see here some people actually they have been over abstracting to even more than 100%, which means that really they are consuming the reserve of the groundwater with any renewal source for that groundwater. So the climate change adds actually another dimension to the problem. And if now you look at the climate change, although there are some countries, they are receiving more rain, but a lot of countries like South Africa, Mediterranean Basin, Southern Asia, they have a decrease in the rainfall. And in decrease in the rainfall means simply that we will have less water resources available. And if now you look at what would be the impact of the climate change, especially for food, and you can see with increasing temperature from 0 to 5 degrees, that will have a negative impact on the crops. And also we have the prediction that there will be more extreme events like flood and the droughts, and also that will not be helpful to produce more food and to feed the expected 9 billion by 2050. And even in some countries like UK, where most of the people they think UK is a water-rich country or a country that receives enough rainfall, but from time to time we get drought events, and these drought events has been already archived, and it has been starting from 1800s until now. We have been really getting one drought after the other, but the frequency of the drought is started now to increase and increase more and more. And the last severe drought we got, it was 2018, 2018. And we had the most severe drought in the history of UK was the 1976. And there are some books actually about that particular event of the 1976. And this is an example how the people in London were queuing to get water from standing pipes in the street, where the rivers were running dry, and there was rationale of the rationalization of the water for people as water supply was cut from going to the houses. So for all of that, we have a limited water resource, and the concept of the Nexus, we need to improve the water use efficiency of the water and energy, and also to maximize the output and to minimize the input. So the water use efficiency and water efficiency in general for irrigation, you can see at the reservoir, maybe you lose a lot of water by evaporation there. That makes the storage efficiency about 70%. And moving the water from the reservoir all the way to the field, you lose water during the transport, and the efficiency goes down to 35%. And that's something really we have to do something about it, and we have to improve that efficiency and reduce the losses and to maximize the use of each drop of water. And here is example from a farmer near where I live, where he has been using solar panel floating on his water reservoir that he's using for irrigation. It has double benefit. One, it would reduce the losses by evaporation. And second, it also gives him a source of power for his dairy products. We can also improve the water use efficiency by knowing how much water we need to apply and when to apply, because always the agronomists and the irrigation practitioners, they struggle with the amount of water they should really apply. So here in an experiment in north of Italy, in project funded by the EU, we used 3 instruments, edecovariance, to measure the actual evaporation, scintillometer, also to measure actual evaporation, and we used also Cosmos to measure the aerial-based soil moisture in order to estimate more accurately how much water we apply. And this is example of the scintillometer, where we have a transmitter and receiver at the end of the transect, and they can be at any length. It can go up to 10 kilometers. And we send really optical infrared with micro radio wave from the transmitter, and we receive it there at the other end. And during that transmitting, we actually look at the change in the air density due to the evaporation from the different evaporation, and we do the analysis to obtain the actual evaporation. And when we look at the footprint across the transect, you can actually see here that this is the contributing area to the actual evapotranspiration, and this is the least contributing area. And we can actually analyze the data comes from scintillometer, how much actually each crop contributed to the total actual evaporation, And here across the transect, we can see that wheat has been contributing like 44%, and maize 35% of the actual. We can base our irrigation more precisely for each crop, different from the other. And this is here the results of what we got from the EDI covariance and also from scintillometer, where we can actually look at this important graph. Most of the people, they estimate the crop water requirements based on the reference evapotranspiration ET node, or multiplied by crop coefficient KC to obtain the ATC. And we compared what we get from the EDI covariance, which gives direct measurements of the actual evapotranspiration, and the scintillometer, and we found actually the ratio of what we get as actual evapotranspiration from the instruments represents less than half of what we calculate from the commonly used Penman-Monteith, the modified equation of FAO 56, and also from the ET node. So basically, when we accurately measure the actual evapotranspiration, we can add less water than when we use the equation that based on meteorological data like modified Penman-Monteith, because actually these equations represent the atmospheric demand for water rather than the crop and soil water demand for water. And that's the big difference between the two methods. So my recommendation from that is for people that working with crop water requirements who would like to determine accurately the amount of water to apply, they should consider any method that actually look at the crop and soil water demand rather than a method that relies very much on meteorological data, because this meteorological data represents the atmospheric demand rather than and the crop and soil demand, and there is a big difference in the amount of water. Should we accurately measure this, we might be able to save almost half of the water that actually we apply. And myself, I have seen a lot of papers where people they irrigate for less than the 100% of the crop water requirements calculated by modified Penman-Monteith, and you obtain the same yield when they apply 60% of that value. It's because simply what actually they apply is really related to the atmospheric demand, which most likely to be related to the potential crop water requirement rather than the actual crop water requirement. The other method that also we used here is the soil moisture deficit. Soil moisture deficit can be measured by soil moisture sensors. However, those soil moisture sensors, most of them are point based, and the soil heterogeneity actually gives us a different variations across the field. And this method can give us a more integrated value for field, and it would sense the soil moisture at the scale of 300 to 700 meter radius. And it is completely safe based on the cosmic rays, and would actually give us a good results for a larger area. And here the results we obtained from the project Water for Crops, where you can see the top graph is the soil moisture content, and then you can also see how the soil moisture respond sensitively to the amount of rainfall. When you have a rainfall, you can see the spike there and a big change. And also if you have a dry period, you can see a big drop. The bottom graph, which is the most important one for irrigation, and this actually here you can see the soil moisture deficit given a color code. When it's green, you don't need to irrigate. And when you have amber, you have a very mild stress. And when you have it really red, then you will have really to irrigate. So this can be operational, or the Cosmos probe can be linked to a system that can be operational, and then you could use that to actually determine how much water to apply and when to apply. And there are some references here. And also Wiley produced a press release about these methods as a methods or technology that could actually save a lot of water. And the Cosmos new now tools would include now a mobile system. You can actually pull it by a Land Rover and you go across the field and you can have more of aerial based values. Another thing really to cope with the demand for increasing the food production is to look at increasing also the water supply. And in water supply, we need to harvest the rainfall at different scales from even the roofs of buildings, schools, houses, public buildings. And also you can harvest that water on micro catchment, and you can get more catchment to be terraced, and you can grow really food on those terraces. And on large and big macro catchments, you can actually direct that water to the lowest point, which is a valley. And in that valley, you could actually start your agriculture based on how much water really you harvest from the runoff across. And another way, of course, of getting extra water supply is to harvest the fog. And the other thing is in Brazil, they have underground dams where actually they have they dig there, a trench there, then they put plastic sheets to separate two sections of the land, and this is what you see after they put those plastic sheets, which actually doesn't allow any horizontal movement of water between two sections of the land, and the water will be kept between these two sections for the plant to take the water from there. So basically, it's a water storage per section system. Another thing that we also work with is to have in rain-fed areas in particular, that we create those jays or pitting holes, and then when the rain comes, they get filled, and they can also supply small trees with the water needed. And this is another example from Cambodia, where the students during the school lessons they go and also they do that as exercise. In North Africa, this is Tunisia, for example, and some African countries, like Burkina Faso, they do these bonds, and these bonds also would harvest some of the rainfall to allow trees to grow. Another project I was involved in is to actually to establish some points for harvesting water in mountainous areas where the farmers, they can grow water closer to the reservoirs. So they bring their agriculture to where the water is. And that's another system that really you could also apply to increase the water supply. In terms of irrigation, we also need to use the water more efficiently by selecting the best irrigation system. Sprinkler irrigation is not really the best because you irrigate in between the plants, and that water just be evaporated back. And subsurface irrigation would be better because you will minimize the losses by evaporation from soil surface, and also alternate furrows would also be an efficient system. Then all of them are better than surface irrigation or furrow irrigation. This is an example here of the rice cultivation, and this is paper won the award of ICID at some stage. And here they don't really grow flooded rice, but they allow only 7 centimeters of water height to grow rice in rows. Another thing, of course, is the use of nozzles of center pivot close to the ground would minimize the wind losses by the wind drift, and losses also by evaporation. And at the same time, it has also benefit when you are using saline water or treated wastewater, it's better to have the nozzles closer to the ground, so you don't have salt accumulated on the plant leaves, or you don't have contaminated really water standing on the leaves as well. And at the same time, it would use less water than the conventional centrifugal system. Drip irrigation would consume less water, but surface irrigation also, as you see here, would allow some water to evaporate from the surface, while the subsurface drip irrigation would actually minimize that water losses by evaporation from the surface, which gives you a more efficient and a better use of water. And the subsurface irrigation has been practiced also for cotton cultivation in USA, and it was save actually 75% of the labor cost, and you can actually also use less water. What we used in projects in water for crops, we also used what we call partial root drying method, or PRD. We irrigate the plants and using two drip lines. The plant is in between the two drip lines, and at the time of the irrigation, we only apply the water to one drip line, which would irrigate half of the root zone. And the next irrigation, we allow the other line to irrigate the second half of the root zone. So by this, when we irrigate, we only irrigate half of the root zone at a time, and we alternate between the two. And that would allow actually some mild stress to the plant, but it's not really harmful, and we obtain a good yield. We applied that in 3 crops: potatoes, tomatoes, and maize. And the results of that, we could actually save 26% for water saving compared to the normal drip, and 44% when compared with the sprinkler irrigation system. Some people, they say, oh, the cost of the drip might be high, but here you can have really low cost and low tech drip irrigation system. But it would use less water, and you will get even more yield compared to the surface irrigation system. Also, another thing we have been involved in is to use non-conventional crops. And these crops, they use less water, and also they are more drought and salt tolerant. And they can sometimes also be tolerant to heat and wind. And one of them really we looked at in one of the projects that we were involved in is quinoa and amaranth. And these two, especially quinoa, has been actually growing in Latin America. And it is really for them like the rice for the Asian countries. And it is very nutritious crop. And you can have really the seeds, and you can make bread and cakes as much as you do from wheat. And we had actually here to try to grow quinoa in the UK, although it's more humid and maybe more cold, but it did grow. And now we have one of the students of Harper Adams University, which is agricultural university, managed to get his own business and his own farm, and he's now the main distributor actually of quinoa to the whole UK. And some restaurants nowadays, we offer actually quinoa as part of their menus. Use of non-conventional water resources is another way to also to increase our water supplies and to make good use of the drainage volumes otherwise lost to rivers and to the seas. And that would include irrigation drainage water, brackish groundwater, and wastewater from industry and from mine breweries and fish farming. Saline water in particular really is the biggest source of water. It's almost 99%, while the fresh water is only 1%, and most of the time it is really under the ground. And in so many places it is brackish as well. It's not really fresh, and in some other areas it's non-renewable, like some parts in North Africa. We used saline water to produce tomatoes in Egypt, for example, and in Syria. And we also used it in Malta and Spain for cherry tomatoes. And we got even higher sugar content in the tomatoes irrigated by saline water. And the consumers were quite happy with that sort of tomato. Dubai, the ICBA, the International Bioagriculture Center, they actually managed to grow pale millet with 15 even decimals per meter saline water, and the barley also was about 15. And also they are producing fodder, and they also growing pharmaceutical plants using highly saline water. And also there is another way of doing using the drainage water by recycling the drainage water from one field to another by starting to irrigate the salt sensitive first, collect the drainage water and irrigate the next field that has got plants with slightly more tolerant to salinity, and so on until you irrigate, you collect the drainage and you irrigate the highly saline tolerant plants. So that system actually recycling and reusing the water in every step. In a project of the water for crops, and which involved EcoSat in Hyderabad, we also looked at how we use the wastewater from the brewery, Kingfisher Beer Brewery, for example. And also we have been looking at using the wastewater that comes from the sugar industry. And in India, you have 650 distillers, and actually their water could be used for irrigation, and they can increase water supply quite significantly. In experiment in Egypt, we tried to use the water that comes from fish farming for irrigation, and actually we got a good yield, better yield of wheat when we use that water, and that paper actually won the best paper award 2018 by ICID. In Safir project, we have been looking at smaller communities wastewater use, and we were able, with the help of Danish company Grundfos, to have in situ treatment for smaller communities where we can treat the water and use it for drip irrigation to grow food. And this is really a prototype installation in Crete. We did one in Serbia, and we did one in Italy. And we have been looking for a smaller system for a smaller community where we can treat their own domestic wastewater and use it for irrigation. And here what you can see really is a shipping container. And in the shipping container, we have treatment, and that treatment of water can give it really a good quality that can be used for irrigation. And there was also Icarda, a partner in that project, and they were looking at whether the wastewater can give us a higher production compared to fresh water. And you can see here in the graph that wheat and faba bean and vegetables give higher yield when they irrigated with treated wastewater, because that water still has got a lot of nutrients compared to the fresh water. Models can also be tools for management, because we cannot read every hypothetical scenario in the field. So if we have an idea in mind, we can run it with a model that we trust, and we have been calibrating it before. So you could actually look at that model and you run it with different scenarios. And when you arrive to the scenarios that gives you the best result, then you can apply that to the field as a validation. So the SaltMed model, which I developed on maybe over 20 years, and every year we add a little bit to it, and that has been funded by European Commission through 4 projects, and it is available at ICID website. And the model can actually deal with the processes of evaporation, plant water uptake, water and solute transport under different irrigation system, leaching, all the nitrogen cycle, soil temperature, drainage, crop yield, water use relation, and crop protection, up to 20 fields or 20 treatments. And when you run the model, that's what you can see on the screen. And you can see the soil moisture, soil salinity, soil moisture when you use a multiple drip system. You can see also the dry matter. You can see also the yield, and you can see also the groundwater level. There is also an issue related to the Nexus, which is a crop and food issue. And if you look at the turn of the century, that the number of varieties we had were actually a lot higher than we have now. And if I take the lettuce, for example, lettuce 497 variety, and at the turn of the century, and now if you look down, it just went down to 36 variety. If you look at the tomato, we had 408 variety at the turn of the century. We ended up by only 79. So there is actually a reduction in number of varieties that we had before. And that actually made Darwin to come with his idea that it is not the strongest of the species that survives, nor the most intelligent, but the one most responsive to the change. And it looks like this is something really we need to look at, is to look at improving through the biotechnology the response of the plant to the biotic and abiotic stresses like the heat and width and cold, nutrient deficiency. And we need to look at the role of biotechnology in terms of the Nexus. So we hope from the new biotechnology that they should be able to help us to develop new crop varieties with higher yields per unit of water, and crops with comparable yields but shorter growth periods. We need to develop crops with drought and salt tolerant, high harvest index. We need to improve the crops, so-called C3 efficiency, to the level of the C4 plants. C4 plants are high efficiency, like the maize, and we need all the crops that they belong to C3, the efficiency to be at level 4, and that's the job of biotechnology. And also we need to develop crops with deeper and wider rooting system so they can take up more wood and nutrients. And the crops that don't need replanting. So by this, actually, we could also save time and produce more within a shorter period. And this is example of the crops that the crops that we're looking at with Bologna University, where they brought to Bologna maize that grows and completes its full cycle in 2 months in Canada. And they were looking at the genes of that maize, and they try to grow crops in Italy also with a shorter period. And then you can save more water and fertilizers. This is also another example of biotechnology, the Durham wheat, that more tolerant to salinity, where the Australians, they managed to use an ancient Persian variety, salt tolerant, and to hybrid it with their own Australian variety, and they obtained actually Durham wheat that actually more tolerant. So biotechnology really can help us to use non-conventional water resources and also to save more water and energy. Land management also is important because suitable tillage, like conservation tillage, mulching, leveling, plowing the crop residues, manure application, soil amendments, all actually helps us to reduce the fertilizers input and also water input, reduces the losses. A precise input or low input, precision agriculture is also needed. Monitoring systems also needed to know whether really the plant needs water or fertilizers or not. The agro-environment or wildlife strips at the edge of the field to enhance pollination rate is now really quite encouraged by the Minister of Agriculture in the UK. So they give the farmers actually a good amount of money to allow the strips around the field to be wildlife. Wild flowers, for example. Wild flowers strip would actually encourage pollination and would increase also the yield. And you can see here the reduction will be in soil evaporation, and increase the water availability, increase organic matter, reduce soil erosion, and increase nutrient availability, reduce agrochemicals use and the labor, and also improves wildlife. And this is example of that what I have seen myself in these actually zero tillage fields, where you can see actually the biota is quite active, and earthworms actually quite healthy there. And the benefit of having earthworms is they create actually environment that would allow higher infiltration, good recharge to the aquifer, and also creates a better aeration in the root zone for the plant. So the water actually movement and the air movement actually improves, and also the structure of the soil improves under those minimum or zero tillage. And this is example of the mixed cropping system, which in the UK now is encouraged because it would actually help in improving pollination and cross-pollination and improving the yield. The energy issues in the Nexus, and we need, of course, to have a clean and the green energy. And there is always a competition between energy for food, the energy for food, and also the energy for other uses. So the biofuel crops affects the water availability, because most of the biofuel crops, they are actually water consuming crops. They grow quickly, they produce a huge biomass, and we need to consider the delicate balance between the water, food, and energy security. And this is an example from Brazil, and this is castor bean as biofuel crops. In Brazil also, there is a wide use of sugar cane for ethanol for the cars, and this is actually quite significant increase in Brazil in the last years. And I had a PhD students working with me, or postdoctor. Postdoctor is actually a student, and and she was looking at the impact of the castor beans and sugar cane on the groundwater and surface water, and also running the climate change scenarios. And it's in the climate change scenarios, it is appearing that there will be a reduction in recharge to aquifer and surface water by 2099. And as the time goes by, the reduction would increase. At the same time, changing the land use from arable to castor beans or sugar cane actually would reduce the amount of water that goes to the recharge. So we now started to, instead of biofuel, started to think about wind energy and solar energy. But also some people started to use also the biofuel or bioenergy, which actually takes a lot of water compared to the classical arable crops. And if you see you see that graph, you can see now the increase in the number really of wind energy over the years. It's increasing because it's a cleaner source, of course. And also the companies who are now producing irrigation systems, they started to use solar panel, and there is more than 30% of water in the energy saving possible with that actually solar system center pivot. And this is an example from India as well, where smaller farming holdings, that they can also have solar panel to pump the water to that reservoir for drip irrigation that goes simply by gravity. And also solar panel also as a source of energy to pumping underground water is now on the increase. This is maybe a not very updated slide, but I met the company, and by that time they were able to abstract water from 100 meters deep. But I think this company now must have improved on that depth. So there is another thing actually now is in news is the biogas, and the biogas actually started, or the lead It actually was the Germans, and then the UK now started also to pay attention to use the food waste, and the food waste now is used to produce biogas, and that's actually another source of energy, but also another source of reducing the the mountain of food waste. And this is really an example of the biogas fermentation. And now the precision agriculture for efficient water leveling is important for a better water use distribution and more effective use of water. And also in one of the projects here, we had that telemetry system. We have sensors, and those sensors here, they send really a signal by telemetry system. It's basically like mobile system transmitter to the computer, and then the computer would, if the soil moisture goes beyond certain level, then the control panel would trigger the irrigation to start. And also now you can see a lot of really sensors here provided to the tractors, and when the tractors they move around, so they know really more information about the leveling and other information related to the conditions of the field. And also nowadays they started to use more drones, and those drones they can also sense not only the water need, but also some of these drones they are actually also they look at the deficiency in some nutrients, especially the nitrogen. So really in terms of really Nexus, there are so many things really that can be included in the Nexus work. One is improving water use efficiency and productivity by using suitable and efficient irrigation systems like subsurface, low-level sprayer sprinkler, water saving approaches using novel strategies like deficit irrigation, partial root drying, minimizing water losses using anti-transpiration agents, soil mulching and minimum tillage, reducing the use of fresh water by using non-conventional water resources like brackish groundwater, for example, using less water demanding crops, drought and saline tolerant, quinoa and amaranth, selection of breed of drought and salt resistant crop varieties, increasing water and nutrient use efficiency through smart cropping system, including a rotation, deep-rooted crops followed by shallow-rooted crops, increasing water supply through water harvesting to ponds and reservoirs. Also, the use of novel methods to accurately estimate crop water requirement, when and how much water to apply, improving the social capability, reducing the vulnerability, reducing the drought risk hazard, and improving the ecosystem resilience. Field scale model application for water, crop, soil, and fertilizer management. Models can be used as management tool to optimize resource input and maximize output. Developing and using renewable energy system like wind, solar, sea tide, and hydropower. The benefit of the Nexus implementation at field level includes the improvement in water productivity, agronomic and engineering management, improved energy use efficiency, improved agricultural water management, for example, rainwater harvesting and soil water conservation technologies, improved crop varieties with high water use efficiency and improved agronomic practices, for example, intercropping, micro irrigation system, drip and subsurface, in place of macro irrigation systems like overhead and sprinkler type for irrigation, and practicing deficit irrigation to increase water productivity. And these are important in achieving the sustainable development goals number 2 and 6, 12 and 13. And as you see here, that number 2, it's very much related to the hunger and to hunger. And then you have here number 12, responsible consumption and production, and number 13, the climate action, and number 15 is the life on the land. And then at national level, the benefit of the Nexus implementation include adopting more holistic approach in planning. For example, if national targets is to increase the area under irrigation, then the plan should include matching available water and energy resources. And from my experience in some countries, the Ministry of Agriculture, they don't to the Ministry of Irrigation and Ministry of Energy. And sometimes the Minister of Agriculture, they come with a plan to increase the land for food, to increase the arable lands without consultation with the Ministry of Water to ask if they have enough water or not, and without consultation with the Minister of Energy to ask them whether they have enough energy to supply them to abstract the water either from the rivers or from the groundwater. So at national level, the Nexus them to talk to each other and to plan together for such national projects. Also, the integrate plan would require investment, and that investment, of course, is better done at the national level and with the government really planning and contacting the right donors at national level. An illustration of the water food nexus of the Asia Pacific region, the freshwater policy in Japan, the Basic Act on Water Cycle was enacted in April 2014. And that now water policy in the cabinet and involves interagency and the multi-sector coordinating body, and that actually now becoming an integrated management plan for Japan, and the 7 different ministries and agencies are currently involved in the Japanese water management. So it's not any longer a one agency or one ministry to look after water. So the water energy nexus still needs some research, and this is maybe for the young researchers maybe at the university to look at as a point of research. The water energy food nexus is a policy making challenge due to the complex interlink of these resources. Although models and frameworks have been proposed to improve resources policy planning, more sophisticated models are needed to identify practical methods to manage natural resources in an integrated way. The other thing also, or in other words, there is an urgent need for integrated planning and system thinking rather than optimizing the use of one resource over the other. The agriculture sector requires significant more amount of energy as input to production. Yet few water energy food resources planning approaches have incorporated special cropping patterns and the land use by combining energy and water requirements. The land use actually still a weak point in most of these models that supposed to be doing the analysis for the nexus. And that's the special dimension for the issue of the nexus. Policymakers are provided with an effective way to analyze the nexus on aggregated level using macro drivers, but these often omit the complexity of managing the resources at a small scale, where other factors such as climate, geography have tremendous influence on supply and demand. So this is the scaling issue. How can really you scale things to the level that really needed? There are knowledge gaps coming from the incorporation of special temporal drivers as well as the special temporal dynamics of resources availability. For example, the rainfall is, as a part of the climate change, is more dynamic, is over time. And actually, most of these models, they look at the existing, maybe the existing or the current climatic data of the rainfall, but it should be taking into account the spatial and distribution of the rainfall, the temperature, and the other factors that affect actually the nexus. I would like to stop here and thank you. I hope it went okay. And the line was clear.
Was very clear, Dr. Raghav. I'm very glad. So you shared our audience, your expertise, experiences. Now I think Uma, are you arranging any questions now?
Sir, we have few questions in the chat box.
Yeah, please.
So one from Srinivas Reddy, sir. He's saying that, sir, it is very informative and I need a clarification on the availability of fresh water in the future. I presume the freshwater availability in quantitative terms will be increased with changing climatic conditions, increased global temperature. Please clarify.
Well, the question here assumes the freshwater availability in quantitative terms will be increased with changing climate conditions. Maybe, but the temperature, well, as I mentioned, there are some countries will get more rainfall, but even with the increase in the rainfall, these countries will get increase in temperature. Temperature will be always on the increase, while the rainfall might increase in some area and decrease in another. So sometimes you get the benefit from the increased rainfall actually will be balanced by losses of water by evapotranspiration due to the high temperature. And that's actually what we found in some studies here in the UK. Sometimes you feel that here in the UK we have Scotland in the north, and I have been doing a drought study on 7 catchments, including Scotland in the north and some other catchments in the middle of the UK and others in the south. And I that the Scotland might get more rainfall, but the losses by evapotranspiration due to the high temperature actually outweigh the gain by the rainfall. So in theory, we don't really expect much of increased water resources globally. And contrary, because the population increase will actually will absorb any increase in the rainfall. Add to that the losses by evapotranspiration as well. So there is really, you cannot really talk about one element without the others. When you talk about increasing water resources, you have to also to see whether the climate change will have impacts, the population growth will have impacts, and what actually standing against the gain by increasing rainfall is the increase in temperature and the increase on population growth. And that can actually take any increase of the rainfall away, really.
Thank you, sir. There is another query from Dr. Satyendra Thakur. Is wastewater suitable for fish farming? And which type of wastewater, like industrial or food processing plant wastewater or any other? Please advise.
It depends on the type of wastewater, really. When we talk about the food industry, the water used to wash, for example, the the vegetables before they can them or before they put them to the food, the supermarket, this water is still clean water and can be used. The water for breweries that produce beer, they only used to wash the barley, and that water actually is clean, can be used for fish or for irrigation. Um, it depends really. The only concern for me if you use industrial wastewater. Industrial wastewater has heavy metals like mercury, cadmium, and so on. And this is the one that really needs a different treatment. And when I was working with the Grundfos, who actually developed the prototype that shipping container um, in situ water treatment, they had special filter for industrial wastes, although we didn't use it because the water was coming from domestic source. But there is actually something that iron hydroxide or something they use as a filter to catch all those heavy metals. So the one of concern is the industrial wastewater. It needs different treatment, but all the water that comes from brewery, from sugarcane industry, from agro industry, food industry, all those waters are clean, and sometimes you feel sorry that water actually went to waste, and they can be used.
Thank you so much, sir, for clearing the doubt. There is another query from Sai Lohita. What kind of plants are suitable for growing using fish wastewater?
The paper that won the prize for 2018 best paper, the fish actually drainage water was used to grow wheat. So the water has been used for wheat, and I expect that that water can be used for any other really crop, not especially wheat. It should be okay for any type of crop. So the water has got organic matter and from the fish, of course, wastes and so on. And it's really useful, and it has got a lot of nutrients. There is no really restrictions in my mind on not using that fish pond water, because I believe that the breeders of fish water, they don't really add any nasty chemicals to the fish water, otherwise the fish would die. So the fish actually farmers, they are very good in keeping the fish in a very good condition and very healthy condition. So they are more really caring about the fish than what we think, and they follow the health of the fish, and the movement and how active they are. So really they are paying attention to the health and wealth of the fish. So I trust the water that comes from fish farming, because they would avoid really adding any harmful chemicals to the fish.
Thank you, sir. So, what do you think is the impact of COVID on water, energy, food nexus?
Is that for me?
Yes, sir.
Please fill the feedback from. So I need to
No,
copy.
sir. It is no. It is not there in the chat box, sir.
So this is a form for me to fill. Yeah.
No, sir. This is for the participants.
Okay.
Can you repeat, Uma?
Yes, sir.
What you wanted to ask?
What is the impact of COVID on water, energy, food nexus? Impact of COVID on water, energy, food nexus.
I'm reading here the message. It was such an experienced and refreshing speak. Is that the one you talk about? The last message?
Dr. Raghav, what the question is that what is the impact of the COVID-19 on this nexus? That is the one participant want to know, and everybody is experiencing the nexus, okay, without telling. But your side, they want to hear what is your stake on the nexus impact on COVID impact on the nexus, please.
The Nexus impact um, is actually related most of the time to um, the food chain, uh, because some farmers, they couldn't get people to harvest their crops, and this is really was clear here in the UK. They couldn't really get farmers to harvest crops during the COVID, and also the the food industry couldn't really get things to their field because of the lockdown. Under the lockdown, there are so many things really restricted the movement. So the COVID had actually negative impact on the food chain from the field, where the farmers here, they couldn't get um, the laborers, because most of the farms here are large really. The minimum really economically viable farm here is about 10 hectares. And most of the farmers here, they don't have laborers living on the farm. So they have to come from somewhere. And UK was always famous for getting seasonal laborers from abroad, from Romania, Bulgaria, from some members of the EU, poorer countries. And they come here to harvest strawberry, for example, and the strawberry of last year was harvested and left to rotten because simply there was restrictions on flying of those seasonal laborers, and the local laborers here, they are not really um, in large numbers, and maybe not keen on agricultural work. Um, so there was really a lot of reduction in the labor market here for harvesting the crops, and that actually created some shortages in the UK, and also not because of the local production, because also the cargo coming with food from outside UK was also affected. From we get some fruits from, for example, and vegetables from Kenya, and also because of the coronavirus and the restrictions in the airports in the UK, and this actually was also in a short supply. So the whole actually food chain was affected by coronavirus negatively, and that's something maybe ICID should really and have been pointing that out to the Secretary General, that really we should look into it together with the World Bank.
Thank you, sir. So there is another query from Dr. Yamuna. She's saying that it was such an experienced and refreshing speak. I'm glad that I have attended. I have a question. She's asking what are the speaker thoughts on technologies in saving water for the country like India, where most of them are fragmented and rain-fed lands.
The technology and for crop water requirements in particular, it came from really simple. I am editor for Agricultural Science Journal of Cambridge University, and I received so many papers from young scientists, and they all came with comparative study. And some of them, they say, well, um, I applied that equation of Penman-Monteith, the modified, or I applied Hargrave equation, or Brennick-Leder equation, or Penman equation, and so on. And I applied the value, I obtained from the equation, and also as water. I also applied 50% or 6% of the amount calculated, and I got the same yield. And therefore, I can save 40% of the water. And really, I have been thinking about it myself. There's no doubt, of course, in my mind, that the young researcher who obtained these results is true in what he says. And it's measurements. You cannot really not trust something measured. So based on my understanding that measurements speaks louder than calculations, I started to think about if I have a project, I will really put some thinking about it and why actually we are getting the same yield at 60% crop water requirements compared to 100%. And then I came to the conclusion that we are actually, in these equations, we are using meteorological data, temperature, relative humidity, and so on. So the idea came to my mind, if we are using meteorological data, basically we are looking at atmospheric demand for water. If I talk to the atmosphere and the atmosphere would talk back to me, if I ask the atmosphere, do you need water? Atmosphere would reply to me, say, yes, I have relative humidity 80%. I can still accommodate 20%. That's in case if the atmosphere would reply to me. But no one of us in all our career talk to the soil or to the plant. No one asked the plant, do you need water? No one asked the soil, do you need water? No one. No one of us. And this is the rationale behind my thinking. If I get the resources and a project just to investigate the atmospheric demand versus the crop and water and soil demand for water, I might come to the conclusion. So it took me quite some efforts really to come with instruments that they measure the actual evaporation, not the potential, it's actual. So you have a sensor there, and those sensors, they measure the evaporation flow. And this is something you cannot doubt as evaporation flow between two sensors. And that's really how I came to that important paper. And I think when I put these two papers for publication, it was immediately picked up by the Wiley publisher in USA and put immediately a press release. And I got so many interviews and so on because of it. But I think it was really the motivation came from the young scientists, not from me. The young scientists pushed me to think for them as why actually they can get the same yield when they apply 60% of the amount calculated by meteorology-based equations. So maybe I was lucky enough to have money to do it, but you can do it with less. If you don't have the scintillometer or radiocovariance, look for any method that can actually measure the actual soil evaporation. For example, you could use lysimeters. And the lysimeters, these can be any container. Sometimes the waste container that we put outside the house for collection. Some people, they use that. And they can do that. And Harper Adams University used actually a waste bins container as a lysimeter where they can control how much water goes in and how much water goes out. So they have a handle on what goes in and what goes in, and out. And you can actually have these data and the results obtained from lysimeters, compare them with what you calculate from the commonly used equation, and try to work out a correction factor. And they keep using the commonly used equation that you are used to based on meteorological data, but have in mind a correction factor to reduce what you get from the equations to the actual level of lysimeters. If you don't have lysimeters, you can look at the soil moisture in the soil profile. So the soil moisture is a good indicator of what's happening in the root zone. So if the soil moisture reduces by time, then you can actually, between one date and another, you can calculate how much water is actually consumed by the plant in terms of uptake and then lost by transpiration. And if you do that for a short period, work out a correction factor based on that. And then you carry on with what you use as common method and correct what you really you obtain. So there is no need for you to go to the Rolls-Royce type of cars if the Fiat can actually work fine. or the tuk-tuk can also take you from A to B. It's the same as the Rolls Royce, as long as it takes you from A to B. So as long as really you have the money, you can use these fancy equipments. But if you don't, there are so many ways that really you can obtain the actual evapotranspiration or actual soil moisture use and make a correction factor to what you use. But you have to have in mind what you obtain from the equations based on meteorological data. It doesn't really represent the crop and the soil water demand for water.
Thank you, sir. Sir, with your permission, we have one more query, sir, in the chat box. How to make best use of domestic wastewater for crop production? From Professor Shailaja.
How to make best use of domestic wastewater for crop production. Well, my experience really with the best use of domestic water is that it requires certain really management. Number one, when you actually treat domestic wastewater, you treat it not to the level of drinking water. So that would reduce the use of energy. So that's number one. So you don't really need to, treat the water to the level of really drinking water. So because the soil is a filter on its own. And then that's number one. Number two is you have to use the crops that shouldn't be used fresh, like salads, tomato, for example. But if you are going to use salads and so on, you have to use subsurface drip irrigation because we don't want to get the leaves or the fruits in contact with treated wastewater. So you have to use a subsurface drip line if you want really to use fresh vegetables like salads or tomatoes or coriander or any of those herbal vegetables. So you have really to have the proper irrigation system. For that, don't use a sprinkler. My recommendation, whatever you do, don't use sprinkler irrigation with treated wastewater, no matter the degree of treatment, because that's harmful to your health. Number two, if you are irrigation engineer, you have to have equipments, protecting equipments when you are in the field and using that water. And the best thing to do is to use subsurface drip irrigation. So by this, you don't have any contact as an irrigation engineer or irrigation practitioner. You don't have any contact with your skin when you are using treated wastewater. A lot of people, they find it easy, and I found that in Tunisia, to irrigate fruit trees. And because there is less vulnerability from using the water on the fruit trees. And that's what the Tunisian people, they use. Most of the domestic wastewater goes to either the landscape, in the streets, the trees that they grow on the streets to give nice shade, and in cities and so on. So they can use that for the landscape, also there, but not in the sports field where the children and the others, they play sports. They don't really use treated wastewater because that's also, if any child would fall on the grass, the lawn in the field, might also get in touch with unnecessarily contaminated water. So there's so many really reasons that we have to be careful. But if you are using it for food production, I wouldn't use sprinkler irrigation. That's number one. I wouldn't use also surface irrigation. I would only use drip irrigation and subsurface to the wastewater. I hope I answered your question.
Thank you, sir. We are getting few more questions. If you permit, sir. I think we have already extended the lecture by 10 minutes. If you permit, we have few more questions, sir. Otherwise,
That's fine.
depends.
Uma, you take 1 or 2 hours, okay? Otherwise, okay? Raghav may be getting late otherwise.
No. For me, it's 10 minutes after 12. It's too early for me.
Okay, fine.
Take your
Thank
time.
you so much, sir.
Take your time. No problem. No
Thank you
problem.
so much. There is one query. Saving water by irrigation, half of the root zone, is good practice to save water and good method to use water efficiently. But may I please know its relation with following aspects: soil type, crop, time of irrigation in crops, and so on.
Soil types, crops, time of irrigation. Yeah. Well, when we started this, we actually, it goes very well when you have the plants are at a proper distance from each other. So it works better. If the plants, for example, that not too crowded, so really you can give the plants the right amount. And we use that for potatoes, and we use that for tomatoes, and we use that for maize. Because with these plants, we could actually space them at like 20 centimeters from each other. So, and we can put the drippers at the right distance from the plants, like halfway. So, so put the plant in the middle, and then you can have 10 centimeters on each side, for example. So it goes with the spacing between the plants. So we need to have plants not really too dense. Like here, I have here in the field in front of me, behind my house, we have barley, for example, and really there is no spacing at all. It's just a complete carpet. If you look at the field, it's complete carpet. So it works better with crops that they grow in rows, and there is enough space between the plants to place the drippers at the right distance. As for the soil, we didn't try it in the sandy soil, and I feel that it might not work well with sandy soil. And it is really something that it depends on the percentage of the sand in the soil. If really it's a sandy, like desert sand, the PRD might not work at all. So we got to be careful with the soil texture, because what we need really in the PRD, we need to have a horizontal movement that can cover half of the root horizontally. And if you have sand, what happens is that in sand, the vertical movement of water predominantly vertical, not horizontal. So what you really get is that the water moves quickly downwards without really having a residence time to spread crosswise to cover the root zone. So my fear is that when you have really a soil with high percentage of sand, the PRD might not work because the horizontal movement of water will not really be good enough. So I would maybe not apply the PRD on sandy soil straight away, but you can have a trial in a small plot and have a look to see if really you get enough horizontal movement or not, and simply just you cut across with the soil and have a look at how much the area wetted. And in some cases, in my early days, I used the methylene blue dye. I add methylene blue dye to the irrigation water, and then I cut across the soil to a depth of the root zone, and then I look at the color. If the color has changed, sometimes I added fluorescent dye, and sometimes I added another red dye. I forgot the name of that red one, but there are things that I had to do to make sure that the water movement was good enough to supply the roots with enough water. So you can actually do that experiment before you apply PRD, because I have always suspicion that the horizontal movement in the sandy soil might not be good enough to cover half of the root zone in each irrigation. Time of irrigation for the crops, it depends really of you. If you are using drip irrigation, which is mainly the best for PRD, I think the difference from people can use PRD when you are using furrow irrigation. So you can irrigate one furrow, say today, and the next irrigation, maybe 10 days from now, they irrigate the other furrow. So they leave one furrow dry and one furrow full of water. And the next time they add water to the furrow that was left dry, and the one that was full of water will be left dry. So they irrigate or an alternative way the furrows. And if you are irrigating, applying PRD using a furrow irrigation, then the time of irrigation will depend on really how frequently you irrigate by furrow, which usually takes about 7 to 10 days every time you irrigate, because it adds huge amount of water. But when you are irrigating about drip irrigation, the drip irrigation frequency between 1 day and 3 days on average. And in this case, yeah, that would be the how really you schedule your irrigation and based on the irrigation system.
Thank you, sir, for explaining and clearing the doubt in an elaborated manner. Thank you so much. Larry, sir, any closing thoughts?
Yeah, if no questions, just I will say a few words. In fact, this is wonderful to have today Dr. Raghav. In fact, I know him for last 13 years. And being the secretary of the work group, where he is the chairman, and I learned a lot and experienced all these years. And today he is the president for International Commission on Irrigation and Drainage. It was a wonderful presentation, Dr. Raghav, right from the concept, the theory involved in the practices, also science behind it. In fact, your models, your experiences, everything you shared. I'm very glad and thank you on behalf of the university. In fact, so many, I was told that more than 300 people registered, and it was also live streaming, and all our people got benefited. And in fact, he is also advisor to Karnataka government on certain issues. I thought Dr. Raghav will share something, okay, because of other things, I think he has not put it. One picture you put on solar powered micro irrigation. Dr. Raghav, I am very glad to tell that picture was mine. Okay, that was our research at Bapatla. Okay, when I was working there, I am very glad that picture found a place in our presentation. And I personally invite you to this university one day, whenever you are making your visit to India anytime. And definitely you have to come to our government about our ICID Congress. We are preparing for that. When you are coming, we will be meeting the Honorable Chief Minister and other officials. At that time, we will be visiting our university also. Definitely keep in mind next time whenever you're visiting India, please have one day reserved for that. And on behalf of the university, I thank you once again. And it's really a pleasure to have you here during this afternoon session for sharing your experiences. That's what ICID. I thank you, Dr. Raghav. Again, thank you very much.
Thank you very much, Dr. Yela. And it was always a pleasure working with you in ICID. And I have been always having really a pleasure working in India. I had 2 projects in India and with ICRISAT and Bangalore University and so on. So India for me like home, When I'm there, really, my friends like you, they make me to feel home, and I always have a pleasure to be in India. So I hope that the time will come that really that I will be visiting you there, and I hope India will recover from the current really coronavirus storm, uh, because it's the news here in the UK is really not very good about what's happening there. But we have been subjected to that as well. We have been really subjected in the UK. We were the highest infection rate in whole Europe. And there was also a time that we had the highest death rate in Europe. But there is always light at the end of the tunnel. So don't despair, because I think that thing can be under control, and I'm sure the country will come victorious out of it. I would like really to thank you very much for inviting me, and I wonder if that will be recorded and put on YouTube or something for some other young scientists to benefit from. Are you recording this and be able to put it on YouTube? And if you can give me a link, then I can ask the ICRD to put it there for the benefit of other young scientists. The other thing, I also would like to thank you and university for offering me an honorarium for that lecture, but I would rather prefer really to you to buy a couple of books or something, my name, put them in the library from me to the students of the university. It's always I care about the young scientists, and I would prefer that this money that you are offering can go back to them. Thank you very much for the offer.
Thank you, Dr. Raghav, for your kind words and your concern for the country. And definitely, we hope that the things will improve, and we will be carrying forward with all our activities in future. Thank you very much for your time and your concerns. Thank you very much. See you.
See you. All the best. Thank you.
Thank you, sir.
Thank you.
At the outset, I would like to extend heartfelt thanks to Sri A. Vishnuvardhan Reddy Garu, Honorable Vice Chancellor and IDP Leader, and Dr. A. Pratap Kumar Reddy Garu, Dean of Agriculture and Principal Investigator of IDP, for their endless support and guidance in all the IDP activities. On behalf of ANGRO and IDP team, I extend my sincere thanks to Professor Dr. Raghav for his outstanding presentation. Thank you, sir, for enlightening us about water, food, energy issues, and also how to implement an integrated Nexus approach and benefits of the Nexus at field level, national level, and what are the research needs in this aspect, and also different models as tools for management to optimize the use of input and obtain maximum output. Thank you so much, sir. Your presentation was so incredible that I am finding it difficult getting the right words to express my gratitude to you. Thank you very much. Special thanks to Dr. K. Ella Reddy Garu, Dean of Agricultural Engineering and Technology, for his gracious presence and sharing his valuable thoughts. We were able to arrange this lecture because of you only, sir. Thank you for all the support and guidance, sir. I also thank all the university officers for their gracious presence. Thanks to IDP team at university and college level for their continuous support, and expect the same support in our future activities also. And big thanks to all the participants, distinguished faculty, scientists, dignitaries from other universities, and students for your patient hearing and active participation. It is the audience like you that make the presentations awesome. I remain most grateful for the rapt attention with which you sat through this lecture. I'm confident that you have learned something from this. Thank you for your time and have a wonderful time rest of your day. Thank you so much. Thank you once again.
Thank you very much. Keep in touch. Thank you.
Thanks.
Bye-bye.